In the previous video, we wanted to know an approximation of the distance traveled if the rate was given by negative t squared plus 49. And chose to subdivide the time interval into 50 equal pieces. And so we're going to use a spreadsheet to calculate this value, since it would be way too painful to do by hand. So let's write down a few of the key things we need to know for our calculations. First, we need to know the length of our interval, and that's 7. That's how long it is. We need to know the increments of time we're going to use, and that's 7 divided by 50, since we're subdividing into 50 intervals. And we need our formula. R is equal to negative t squared plus 49. And now we'll be able to use the sum function in the spreadsheet to calculate the estimate. So let me write down, using sigma notation, the total distance will be the sum from I equals 1 to 50. And what's our function? So it's going to be negative xi squared plus 49. So these are the individual summands. We're going to add these all up, where x sub I is equal to I times delta t. Okay, so let's open up the spreadsheet, and here we have our spreadsheet. So I'm going to label some things. We've got the length, which we know is 7. We've got the change in our intervals, which is equals 7 divided by 50, or 0.14. We have to compute our values for t, our values for r, and then we'll do r times our change in t, and finally we'll get our sum. So for t, our formula for our input is, well, first off, the first time point will be 0.14. So I'll just put equals that. Now for the next time point, it's going to be 1.4 plus, or 0.14 plus 0.14. So I'll say this equals the previous cell plus this cell here. Now I'm going to slide this down, so I want to make sure that I don't move off of this cell here. So to freeze it, if you've never used Excel before, you can use a $sign there, and this says to always use cell in row, or always use row 2. That's 0.28. And now I will slide this down, and it's going to be quite a long list, so keep sliding until we get to 7. There we go. And now R, our formula for R, if you recall, this is equal to 49 minus t squared. Which is, in this case, that value. And then now I can slide it down. That'll copy that formula, always using the value to the left. And we see here's our value for our function. Now, finally, we need to do that value times our length of each interval. So this is equal to this value times, again, our change in t, which is that. But again, I'm going to slide down. I don't want this to go off that cell, so I will use the $sign to freeze it. And again, scrolling down, this will recursively use that formula. And now finally, what is the sum? So this equals the sum of, and I'll highlight all of these cells. Oops. And we see that we get 22.5 or 225.2138. So coming back to our blackboard, we can write down that this total distance is equal to 225.21 centimeters. Great, that's with 50. Why stop at 50? Let's do 100. Let's take a look at what the graph would look like if we did 100 intervals. And we see that using 100 intervals in which our change in time would be 7 over 100. And just from the graph alone, we see that this is an incredibly good fit. We'd have to zoom in really close to see that error. And so the total distance, and using summation notation, would be I equals 1 to 100, 49 minus I times delta t squared. And again, we can go to our spreadsheet to evaluate what that sum would be. So now we need to change some things. The length has stayed the same, but our change in time is no longer 7 divided by 50, but 7 divided by 100, giving 0.07. Our time points are going from 0714, so that's so far so good. But now I don't have enough data points, so I'm just going to take all three because I've already put the equations in. Everything's good. I just need to scroll down and get the 100 cells. Not quite there. There we go. So now we're at the end point, and our sum is not using the correct number of cells, so I can come down and see what the address is. That in this last space, this is E101. So I want to go from E2, that's this cell here. So I want to go from E2 down to E101. So I just can change it right here, 101. And now we see that the sum we get is 226.9, we can round that off to 95. So going back to our blackboard, we can say that this is equal to 226.95 centimeters. And we should be feel pretty good about this estimate. This is a good estimate. I shouldn't have written equals, but an estimate. There's a good estimate of the total distance, but it's still going to be an underestimate because we can see we're still missing places. Let's, just for grins, I'm not going to do the calculations, but just take a look if we divided the region into 500 pieces. And now if I divided my interval into 500 pieces, my delta t would no longer be 7 over 100, but it would be 7 over 500. And I could go to the Excel spreadsheet again and calculate that sum, but I won't do that to you. But you should be able to recognize from this graph that that is going to be an excellent estimate. I mean, we can't even see the error. The resolution on this computer is not even good enough to show the differences between the curve and the heights of each of these tiny rectangles. In fact, they're so skinny that I can't even see where one begins and the other vanishes. So 500 is a very small number, and this would give us a really top-notch estimate. Of course, this is math, and we have infinitesimals at our disposal. So what would happen if we were to divide this into an infinite number of intervals? So if we took some hyperinteger, say, and divide it into an infinite number of integers. Well, I can't graph that because we don't have the ability to graph in the infinitesimals, though it would look something like this anyways, visually. Um, but how can we approach this? So let's do this. So instead of dividing the time length into a finite number of pieces, let's let h be an infinite integer. And so our width of each time point would be 7 divided by that infinite number. So this is an infinitesimal. Our individual time points will still be I times that width. And our function is still 49 minus t squared. So then the total distance should be approximately this sum of my function. So it's 49. So at each point, I'm going to put in I dt in for t. So this will be I dt squared. And that whole thing, so that's the height of the rectangle times its width, dt. So now I can't go to a calculator or a spreadsheet or anything and compute this because I'm doing it an infinite number of times. So we're going to have to use math. And we've worked with Riemann sums a little bit. We can distribute this dt through. So I equals 1 to h. It'll be 49 dt minus, we've got an I squared, a dt squared, and this will come in. So it'll be minus I squared times dt cubed. So this is the whole summand. Now sums can distribute across this. So I get the sum from I equals 1 to h, 49 dt minus the sum I equals 1 to h, I squared dt cubed. Now this first summand, notice it's just the constant. It's 49 times dt. There's nothing changing here, and I'm adding it to itself an infinite number of times, this many times. So that should be 49 times h times dt. And here I've got a dt cubed. It's also a constant, the same value being multiplied by this function, so I can factor it out of the sum. So it'll be minus dt cubed times the sum I equals 1 to h of I squared. So now we've got to get a handle on what is the sum of this guy. And so I'm going to put a check mark here. We'll come back to this and just write down this fact that the sum from I equals 1 to n of I squared is equal to n cubed over 3 plus n squared over 2 plus n over 6. Now, I don't expect you to know this off the top of your head. In fact, here's a link to a website that will kind of demonstrate through a nice geometric argument why this should be the case. Typically, this is actually written in this form. If you combine these fractions, you get n times n plus 1 times 2n plus 1 over 6. And though this form right here is going to be better for our purposes. Anyways, check out this link for an explanation of why that should be true. So coming back to our problem at hand, this is equal to 49h dt minus dt cubed times the quantity n cubed over 3 plus n squared over 2 plus n over 6. Now, great. We've got, what is this equal to, or what is it even close to? Well, I've got a constant times an infinite number times an infinitesimal. So it's possible that this is finite. I've also got an infinitesimal cubed here. Oh, I put n here. Just reading these should be h's, my bad. Let me correct that. So inside here, we've got an infinite value, but out here we've got an infinitesimal value. So again, this may be finite. It's an indeterminate form. So remember that dt is 7 divided by h. So we'll substitute that in. And we get that this is equal to 49 times 7 over h times h minus 7 cubed, which is 343, over h cubed times h cubed over 3 plus h squared over 6, over 2 plus h over 6. Now here, the h's will cancel, right? So I've got a h here and there, so they cancel. Here, this cube will cancel with that cube. This cube will cancel with that, leaving a 1h in the bottom, and I'll get that canceling there. So I've got canceling going on. So this is equal to 7 times 49, which is 343, minus, so 343 over 3 plus 343 over 2h plus 343 over 6h squared. And now we can recognize that this, because I'm dividing by an infinite number, so this is an infinitesimal, so it's infinitely close to 0. This is an infinitesimal, infinitely close to 0. The other terms left behind are finite though, right? 343 and 343 over 3. So this infinite sum is infinitely close to 343 minus 343 over 3, which is equal to 686 over 3, or approximately 228.7 centimeters. And so we could say that if the rate the object is traveling, if the rate is given by 49 minus t squared, 0 less than or equal to t less than or equal to 7, then the total distance traveled is 686. I'm going to put an equality, so it's 686 over 3 centimeters.